As told, I will go more in depth into crystallization. Here's an example of a crystal, the block shaped in the picture here, and there are some small needles around it. When you look at it chemically, they are totally identical. When you look at the polymorphism, so an X-ray of this one, they are totally identical. But it's just the conditions under which you grow these crystals that makes it that these two forms may occur. So if you do not control your conditions in a correct manner, then you can get a combination of these two, and you have a very broad particle size distribution, and connected to that, of course, also the properties of your material are changing. That means that solubility or dissolution rate can change here. So why do we do crystallizations? Well, one is isolation or purification. We talked about that one. But it is also crystallization of a specific polymorph. So when you know which one you need to have with the right conditions, you also have a look around that polymorph. What is the area in which I can do? What is the temperature range? What are the different solvents that I can use for this specific polymorph? And that you don't get any side effects of amorphous content or other polymorphs which can be there. We look into crystallization of oily or waxy solids, which most of the time it is caused by a very high solubility of your compound. It refuses to nucleate, and crystallization does not occur. You get a semi-solid or even an oily material. These are impossible to handle when you look at normal conditions of producing. So you keep them in solution and you take everything with it, all the impurities and everything you don't want to have, you take it with it to the next step where it might influence your process over there. So if you can have a crystallization of your oil, you remove again impurities, you have a solid, you have a stop if needed, and you can improve your process and the quality of your product there. Crystallization of amorphous, so that is when your material crashes out of solution. Most of these processes result in crash crystallization because the group is added and all of a sudden it does not dissolve in your material, in your solvent at all. So the material that you get does not have the time to grow as crystals and crashes out as amorphous. Crystallization conditions, most of the time it is a more controlled cooling or more controlled addition of an anti-solvent may result in a crystalline product instead of the amorphous one. But we also specialize in the materials that simply grow as amorphous and need a little bit help to crystallize. So a co-crystallization can be there. It can be using solvent, so that is making a sulfate there that is only useful if the solvent is acceptable and not ending up in your final API. Co-crystallization can also be used by other solids, so use something to make sure that you have a crystalline lattice there to avoid amorphous or to avoid an oil. Co-crystallization means that you have to look at the molecular level to see which connections are possible, how to produce an acceptable co-crystal, but also guide it to an acceptable API. There are two other things still there. That is, on the other hand, if you want to stabilize your amorphous, so if your solubility of the crystalline form is that low that you cannot use it as an API, you need to have other options there. Stabilizing amorphous in a polymer lattice can be one of them. But also avoid the crystallization of unwanted polymers. If a certain sulfate or a certain other polymorph is available and you don't want to form it, either because of a patent or because it influences the yield or the properties of your polymorph, we can have a look at how to avoid these polymorphs, but also find a way how to control it and to see that you don't have that polymorph during your crystallization process. What are the methods that you can use? Well, this is a full screen with totally to the left the research conditions. These are mild conditions, they are close to equilibrium, and they can take up to months. In production, well, these are seconds to minutes because conditions are severe and these are totally non-equilibrium. Can we use all of them? Sure. If you have the time to use them, if you want to use them, of course. Can we scale them up? No. For that, we only have a few limited crystallization methods, which mostly are cooling and anti-solvent. Sometimes when you have it in the reaction, you have a reactive crystallization, you cannot avoid it, but you can have an additional recrystallization going on if it is your final product and you need to optimize it. Finally, also some slurrying can be there if you have not the correct form, not the most stable form that you want to have. You can slurry in certain solvents to make sure that you have a homogeneous compound there. So the main thing is only to use scalable methods and not all methods available, because you're not going to use them when you go into production. Cooling crystallization is one of them. What you have here, you start with point A, you have a solution, you cool down and you keep the concentration in solution that stays stable. So you end up with B, which is the point at the solubility curve. At that point there's equilibrium. If you have endless time and you wait at that point, you will get crystals. Most of the time you do not have that, so you cool down further to the form C where you crosses the nucleation curve. C means solids are formed, your concentration drops down and you go back to D, which is most of the time around room temperature, and that is the amount of solid that you can get out. Why do I present this? Well, that's the next slide. What you see is when you cool down that your solubility curve, that one is fixed. You have your material in there and you have your solvent there. That one is something that is also described by most patents. If you have your process fixed already, that means that you cannot change anything there, but that is not depending which form you will get. Nucleation curve, that one is that can be varied because it is determined by crystallization conditions. That is cooling speed, but it is also what kind of material do you use, what kind of impurity level do you have, do you use seeding or not, because then you don't have nucleation at all, but you have just crystallization growth. And that nucleation curve, that one determines which form will be there, which form is accessible. The different forms and different conditions may lead to different polymorphs that you get, but it may also lead to batch-to-batch differences. So to control your crystallization, you need to know what are the possibilities to influence your nucleation curve, how broad is the metastable zone width, that is the area between the solubility curve and your nucleation curve, and what can you do to get the right form each time, each batch. For anti-solvent addition, you can have the same story here. There is a solubility curve which is fixed, and there is here a metastable zone limit, which depends on how much anti-solvent do you add, how fast do you add it, how much time do you allow to have it there, what is the temperature which you use. So that is the same things can occur there. If you do not control the addition of your anti-solvent, you do not have batch-to-batch same form and the same quality material. How do we work here? We determine metastable zone width because it allows you to have an idea how well will this compound crystallize. You determine the solubility in several process solvents in several temperatures to have an idea how well does it dissolve. In these cases, the solubility curve is as noted here in this figure, but they can also be more flat or even totally different when depending on the temperature. Up to now I only have seen this kind of behavior, so we use this one, and you can use cooling crystallization for most of the compounds that we see here. When you measure your dissolution and nucleation temperature at different concentrations, you can have an idea how broad your metastable zone width is and what is the area to play with. If you do it also applying different conditions, so different cooling rates, you get an idea on the different forms that can be reached by this method, or that you have to go to more extreme conditions, which is anti-solvent addition or crystallization. Of course, when you do something like this, you dissolve everything, you get a complete solution, you cool down again, and you get a form. You need to check by X-ray or other means to see if the form that you make is indeed on each temperature the same form. So it cannot be that you just measure this and you know everything. No, you also have to check if you still have the same form, if the craft that you're making there is indeed of that polymorph and not of something, a solvate or anything else that can be there. Next is crystallization process conditions. When you have defined the area in which you can crystallize, you can nucleate your compound, and you have defined already which solvents to use. Here we use the Multimax equipment for the first scale-up. In general, we do steps of approximately 20 times up to 50 times if the process is really going well. You can have a look at the cooling rate if it is still scalable, if applicable the seeding conditions, anti-solvent additions, and optimize these crystallization conditions. At this scale, we may use design of experiments, but this is still on a small scale a parallel screening of what are the conditions to check the optimized crystallization conditions there. When we go to even larger scale, so these are really the process conditions which we have here, it is 1 liter most of the time. You go from a parallel experimentation to single experiments, and from that stage onward you actually producing different batches one at a time. So you have a demo run, you go up to kilogram, you go to the pilot plant. These are the steps that we make, and all the information that is obtained in R&D and in the parallel experiments can be used at this scale. One thing is most of the time not usable, and that is when you say I have to wait for 3 hours at 50 degrees before nucleation occurs. Most of the time when you look at things like time to crystallize, it is not scalable at all, and you need other techniques to check if indeed your nucleation occurred, if indeed at that scale crystallization is at the same stage as before. But all the information that you get can be obtained from the small-scale R&D experiments. So in summary, solid-state chemistry, we have scalable production methods, cooling and anti-solvent, acceptable process solvents, class 3 or 2, or easy to reduce to allow to residuals level, and a material properties, a stable form, and good filtration and further handling of the compound itself. These are the things that we can use and to select one form to take forward and to combine with the process and really have an integration